This is the principle of inductors that you couldn't figure out in 3 years of school, but it's actually this simple. First, we know that when current flows through a wire, it creates a magnetic field around the conductor that wraps around the wire. The larger the current, the stronger the magnetic field it produces. This is Ampere's law. If you weren't dozing off in class back then, you probably also know this. The direction of this magnetic field can be determined using the right-hand rule. That is, if your right thumb points in the direction of the current, then the direction your other 4 fingers point is the direction of the magnetic field. Now, if we coil this wire into a loop, the magnetic field becomes more concentrated. It forms a stronger magnetic field, and it's very similar to the magnetic field of a permanent magnet, which is the most basic inductor. By increasing the number of turns in the coil, we can strengthen the magnetic flux of the coil. We can also change the magnetic flux by varying the current flowing through the coil. Conversely, according to Faraday's law of electromagnetic induction, when the magnetic flux through a coil changes, this changing flux will induce a voltage in the coil. The changing magnetic flux will generate an induced voltage in the coil, thereby producing current in the circuit. Now this gets interesting. A changing magnetic field causes the coil to produce current, and the current itself also generates a magnetic field. So if we place the coil in a closed circuit, when the current changes, what kind of relationship exists between the magnetic field produced by the current itself and the current? Lenz's law further supplements Faraday's law, pointing out that if the current changes, it will induce a reverse voltage in the inductor's coil. This induced reverse voltage resists this change, thereby suppressing the current change. This is also known as self-induction. Take a simple circuit as an example. When you connect an inductor in parallel between a light bulb and a battery, you'll discover an amazing phenomenon when the circuit is closed. You'll notice the bulb lights up first, then goes out after a while. And when you open the circuit, the bulb lights up again, then goes out after a while. Let's look at this process in slow motion when the circuit is closed. The current first flows to the bulb because at this point, the magnetic field in the inductor is still gradually building up. As the magnetic field strengthens, the inductor generates a back electromotive force through electromagnetic induction. The back electromotive force opposes the voltage provided by the battery, thereby resisting the increase in current. This reduces the current flowing to the inductor, causing more current to flow to the bulb, so the bulb lights up. As time passes, the magnetic field inside the inductor gradually strengthens until it reaches its maximum value. At this point, the inductor's internal resistance is almost zero, just like a wire. Current flows directly through the inductor, creating a short circuit. The bulb goes out as a result. If you open the circuit at this point, the current stops flowing. The magnetic field inside the inductor begins to decay, and back electromotive force is generated again. It tries to maintain the current flow, so the current continues to flow to the bulb. The bulb lights up briefly again. Actually, it's very similar to the capacitor we talked about before. Both are devices that temporarily store energy. But inductors store magnetic energy. When powered on, energy is stored in its magnetic field. When powered off, it releases this magnetic energy, converting it to electrical energy and outputting it to the circuit. The inductor's ability to store a magnetic field is affected by the number of coil turns, coil length, area, and circumference of each coil turn, and the magnetic permeability of the core material. The inductor's characteristics are very useful in circuits. For example, paired with capacitors, they can form filters to remove noise from electrical signals. Used in switching power supplies, they can stabilize output voltage. Placed in wireless charging devices, they can magnetically couple with another coil and wirelessly transmit energy. Inductors can even be useful in sound systems, televisions, computers, and automotive electronics.